Hello everyone, welcome back to our lectures for Geography 101 Earth Systems. This is our final lecture for the semester, and to close things off, I wanted to make sure that we talk about climate change, one of the most important subjects of our modern day, and ways that we can solve it, hopefully. That includes topics of carbon sequestration, geoengineering, and climate action to hopefully give you guys a better idea of some of the ways that we can address this problem and tackle it head on. So let's jump right into it and talk about carbon sequestration. So carbon sequestration is a process of extracting CO2 from the atmosphere and storing it so that it can no longer contribute to climate change. And there's several ways to do this. Mainly, it's done by extracting carbon that's emitted directly out of a oil, gas, or coal-fired power plant, but that's not the only way. So maybe the most simplistic and the most straightforward are biological carbon sequestrations, such as planting trees. Trees have adapted over billions of years. The best way to extract carbon dioxide from the atmosphere. And so planting trees is always a good idea of trying to reduce the amount of carbon dioxide in the atmosphere contributing to climate change. So when we plant a tree, most of the carbon that's sequestered actually doesn't go into the leaves, but instead goes into the trunk and branches of the tree, as well as the organic soil matter. So making the soil more organic matter rich. And so that's really the key to a lot of these biological carbon sequestration methods is trying to increase the amount of organic matter in the soil. And so we can see here that currently trees absorb about 11% of the carbon dioxide we emit. And if we were to plant a tree as many as possible in as wide a area as possible, we'd be able to absorb about 66% of the current emissions today. So it's definitely not a catch-all solution. Oftentimes you have to figure out where to plant these trees, and that's not always simple. You might make it harder for farmers to use land or other land constraints with trees. So while planting trees is always a good thing, it can't be the only solution to our problem. Additionally, trees are a huge benefit to society. So trees provide a lot of economic stimulus to an area through prevention of runoff during storms, by increasing property value, making the area look prettier, reducing CO2, cooling the area and requiring people to use less energy for air conditioning, as well as increasing air quality. And all of these are reasons why planting trees is always a great idea. Additionally, biological carbon sequestration can come in the form of carbon farming. We can get farmers to plant crops that absorb CO2 and then plow those plants directly back into the soil so that carbon is retained and can help build the soil organic content. This is a growing field, no pun intended, but it's really helped by the fact that a lot of farming has become more efficient over time. For example, in the last 20 years, cotton farming has increased its efficiency in terms of carbon emissions by 33%. New tactics such as no-till carbon farming have been really useful for reducing the amount of emissions from farming themselves. And so this is one option available for sequestering carbon, although there's only so much farmland and it's not a huge pull on the atmospheric carbon. Maybe the poster child for carbon sequestration is geological carbon sequestration. This is taking carbon coming out of a factory or from the air and storing it in the ground, and storing it in a way that it can be stored long term and converted into a geological process where we don't have to worry about it as much. And there's a number of different places that we can store this carbon. One of them is deep saline aquifers. Saline aquifers are usually used for groundwater pumping, and they also can absorb CO2 fairly well, and so pumping them into saline aquifers can be effective. But most of the time when we pump CO2 into the ground for carbon sequestration, it's into an area that's been previously drilled for oil and has been since depleted. We know that because that area could hold large amounts of oil, it usually has the geological features in order to also hold a large amount of CO2. And so carbon can be pumped into that area. Additionally, it can be pumped into areas of salt beds, such as prehistoric dried lake beds, as well as in unminable coal beds. Coal can also absorb a large amount of CO2. Another type of carbon sequestration or storage is marine storage. So this is when, instead of pumping the CO2 into the ground, we pump it deep under the ocean floor. And so this has a number of problems associated with it. For one, if you don't pump it deep enough and you expect that CO2 to dissolve into the ocean water, you can have ocean acidity increasing. So you have, we talked about this previously, increased absorption of CO2 leads to more carbonic acid, and the oceans get more acidic, which can be a really big problem for ocean life. Alternatively, you can pump the CO2 really deep, 3,500 meters or more underwater, and at that point, the CO2 will stay in a liquid form. There's so much pressure there instead of getting dissolved as a gas. And hopefully it would stay there, although we don't really know. And we don't really know whether it would have huge impacts on the benthic communities of ecosystems living on the ocean floor, or if there's a way, if the oceans were to warm, as they are with global warming, whether that CO2 would eventually get released. So then the last form of carbon sequestration that's often used is fuel conversion. You can use the gas coming out of a fossil fuel power plant, known as flue gas, and pump it through a series of pipes and use a whole lot of water and catalysts in order to convert that flue gas into fossil fuels again, using solar energy in order to move that chemical reaction in order to produce carbon neutral fuels. And this can be a good way of providing carbon neutral fuels to areas that are still going to need a lot of carbon energy dense fuel sources, such as airplanes that can't be converted to solar power as easily as other forms of energy use. So a good video that explains carbon sequestration is this one here, so we're going to watch it now.
Carbon capture and storage has been around for years. There are a few main types of carbon capture, almost all of which happens at power plants, capturing the carbon that comes directly from the plant. In post-combustion carbon capture, the CO2 is captured after the fossil fuel is burned. In this method, carbon dioxide is separated from the flue gas, which includes carbon dioxide, water vapor, sulfur dioxides, and nitrogen oxides, by bubbling the gas through an absorber column packed with liquid solvents, such as ammonia. In the most widely used system, once the chemicals in the absorber column become saturated, a stream of superheated steam at around 120 degrees is passed through it. This releases the trapped carbon dioxide, which can then be transported for storage elsewhere. In pre-combustion carbon capture, Carbon dioxide is trapped before it's diluted by other flue gases. The fossil fuel is heated in pure oxygen, resulting in a mix of carbon monoxide and hydrogen. The carbon monoxide is reacted with water to produce carbon dioxide, which is captured along with hydrogen. The hydrogen can then be used to produce electricity, and the carbon dioxide is stored. Pre- and post-combustion carbon capture can prevent 80 to 90% of the power plant's carbon emissions from entering the atmosphere. This is a big deal. The IPCC estimates that carbon capture and storage has the potential to make up between 10 and 55% of the total carbon mitigation effort until the year 2100. However, this carbon has to be stored somewhere. It is most often stored underground in a process called geological sequestration, which involves injecting the carbon dioxide into underground rock formations. It is stored as a supercritical fluid, meaning it has properties between those of a gas and a liquid. When carbon dioxide is injected at depth, it will remain in supercritical condition as long as it stays in excess of 31.1 degrees and at a pressure in excess of 72.9 atmospheres. Many times, the carbon dioxide is injected into a reservoir which previously trapped oil and gas, since those areas have natural rock formations that help to contain the carbon dioxide. While this might be an okay solution, no one knows for sure what the environmental impact could be if the carbon dioxide were to leak out into the environment in large quantities. In some instances, leakage of carbon dioxide underground has been shown to increase plant mortality, reduce growth, and create potentially severe localized damage to ecosystems. For this to be a viable, safe option, the carbon dioxide would need to remain stored for hundreds of years, or even indefinitely, and the feasibility of this is not certain. Other methods of storing carbon include sinking it deep below the ocean, at depths under 3,500 meters, where it turns into a slushy material that will sink to the ocean floor under that amount of pressure. But this method is largely untested, and again, there are concerns about what this could mean for marine life, and uncertainty on whether or not the carbon dioxide could eventually make its way back into the environment. There have been more promising experiments in carbon storage in Iceland, where researchers have shown that pumping carbon dioxide into volcanic rock underground can speed up the natural process where the basalts react with the gas to form carbonate minerals, which make up limestone. This is an encouraging development, but it has its limitations. It requires large amounts of water, 25 tons for each ton of carbon dioxide buried, meaning this process would be limited to coastal sites. Another is that subterranean microbes might break down carbonate to methane, another powerful greenhouse gas. And while 80 to 90% of a power plant's carbon emissions can, in theory, be captured and stored in one of many ways, what about all the other carbon emitting things in our world? Only 25% of global greenhouse gas emissions come from electricity and heat production at power plants. Transportation, general industry, and agriculture collectively make up around 60% of greenhouse gas emissions. Is there a way to capture carbon dioxide from these sources? Direct air capture has, up to recently, been a largely theoretical technique in which carbon dioxide is removed directly from the atmosphere. Theoretical because doing this on a scale that would even make a dent has historically been ridiculously expensive. Some experts say as much as $600 per metric ton of carbon dioxide. For reference, a typical passenger vehicle emits about 4.6 metric tons of carbon dioxide per year. But recently, a team of scientists from Harvard University and the Bill Gates funded company Geoengineering announced that they have found a method to cheaply pull carbon dioxide pollution out of the atmosphere. They say for as little as $94 and no more than $232 per metric ton of carbon dioxide. This means it would cost between $1 and $250 to remove the carbon dioxide released by burning a gallon of gasoline in a modern car. And not only do they suck the carbon dioxide out of the air with the ability to store it, they will also transform the carbon back to gasoline or jet fuel, creating net neutral carbon-based fuels. While this sounds too good to be true, the methods they use to pull carbon dioxide out of the air is not too different from what has already been done for decades. This type of direct air capture starts with an air contractor. This structure wet scrubs the air by using a strong hydroxide solution to capture CO2 and convert it into carbonate. The hydroxide solution reacts with carbon dioxide to form carbonate ions. This occurs within a structure which is much the same as an industrial cooling tower. The next step involves a pellet reactor where the carbonate ions react with calcium to form calcium carbonate in the form of dried pellets. Then a circulating fluid heats the calcium carbonate pellets to decomposition temperature, breaking them apart to release carbon dioxide as a gas and leave behind calcium oxide. Finally, the carbon dioxide is combined with hydrogen and converted into liquid fuels including gasoline, diesel and jet fuel using the Fischer-Tropsch process. This is a process where a mixture of carbon monoxide and hydrogen are converted into liquid hydrocarbons. These reactions occur in the presence of metal catalysts and typically at temperatures of 150 to 300 degrees. This means the company can produce carbon-neutral hydrocarbons, meaning if you were to burn this fuel in your car, you would release carbon dioxide pollution out of your exhaust and into the atmosphere, but because this carbon dioxide came from the air in the first place, these emissions would not introduce any new carbon dioxide to the atmosphere, and no oil would need to be extracted from the earth to power your car. And perhaps most importantly, for the economic viability of this idea, they can sell the product, which helps offset costs, allowing them to capture even more carbon dioxide to either convert back into hydrocarbons or ultimately store. And backing up their cost estimates of between $94 and $232 per metric ton of carbon dioxide is the fact that they've actually tested the technology in a prototype plant for a few years in Squamish, British Columbia, which offers a proof of concept that's way stronger than simple calculations or computational models. It currently captures and processes around 1 ton of carbon dioxide per day. However, for this idea to work on a large scale, the process has to be cost effective to implement cheaply around the world, without the massive costs of constructing all new factory parts. In the pilot plant, they pulled all of this off by designing a factory based entirely on parts that suppliers could already make cheaply, and by keeping careful track of their emissions and costs at each stage of the design and production process. They are currently seeking funding for an industrial scale version of the plant that will use low-cost renewable energy that will produce 200 barrels of synthetic fuel a day, which they hope to complete by 2021. But how much carbon can they realistically hope to suck out of the air? In 2017, the world emitted about 32.5 gigatons of carbon dioxide. If this technology were built at a scale to suck all that back out of the atmosphere at $93 to $232 per ton, simple math shows that the total cost would be between $3 trillion and $7.5 trillion. That seems like a lot, but many industries are worth more than that, including Apple or the airline industry. Definitely a tall order, but not impossible. For this idea to work globally in pulling substantial amounts of carbon dioxide from the Earth's atmosphere, there would need to be hundreds or thousands of scaled up plants producing hundreds of thousands of barrels of carbon neutral fuel to drive down costs further, in the same way that solar and wind energy costs have plummeted over the past decades with increasing scales. However, to keep global warming to less than 2 degrees, the international target to avoid the most dangerous impacts, we will need negative emissions, not carbon neutral emissions. We need carbon to be taken out of the atmosphere and stored permanently, or the problem will only plateau indefinitely. And if carbon engineering is making fuel from their captured carbon, this is only a carbon neutral plan. But the reality of the situation is that when you are only capturing and storing carbon, there is no market for that. The only way to pay for carbon being captured from the air and stored on a large scale would be government subsidies, and to rely on our governments to solve this problem is certainly a mistake. And at $100 per ton at the moment, there aren't enough carbon dioxide buyers in the market for any other uses to make a dent. Thus, introducing the idea of selling back the carbon as a fuel is a way to fund such an effort. With market demand and money coming in, companies like Carbon Engineering can improve their technology, expand operations, store some carbon, and work towards making sure that less oil is extracted from the ground over time. Critics say that we should simply not be taking the carbon out of the ground in the first place, focusing on reducing emissions rather than capture and storage or capture and reuse. And some worry that technology like this will allow us to think that we have no responsibility to reduce emissions, and it is cheaper to not emit a ton of carbon dioxide in the first place than to capture it. While these are definitely valid points, technology like this can and should play a role in how we tackle climate change. It's unrealistic to think that every industry, every consumer, and every government in the world will change their behaviour in time to tackle the rising global temperatures, as much as we wish they would. And technology like this will go a long way to help mitigate the negative effects of the industries where a carbon zero result is next to impossible, like steel or cement manufacturing or long distance air travel. So this may not be a silver bullet curing the world of climate change, but it is definitely a technology to be invested in as a tool in the toolbox to help solve the problem. And with direct air capture able to operate anywhere in the world where there is air, water, and electricity, every country could, in theory, have their own supply of carbon neutral fuel.
Yeah, so hopefully that gives you an idea of the processes involved with carbon sequestration and carbon capture, as well as the benefits and downfalls. It's definitely not a panacea, and it can't solve all of our problems, but it's definitely a tool that should be used in order to try to reduce the amount of fossil fuels that we need to extract from the ground and instead provide some carbon neutral fuels. So let's take a break there and we can continue on talking about geoengineering and some other strategies to address climate change in the next video. All right, see you guys soon.